Construing exploiting agency. I'm just give you a moment to set up. So he just was just setting up, and we'd just like to thank our translators for doing a great job. Thank you very much.
Well, one of the interesting things I think about coming to a conference like this is you learn so much on the fly that you almost wish you had the benefit of previous talks before you start. So there are quite a lot of things that I want to talk about that relate to themes from Ivan's keynote this morning, things that Dave was saying a bit earlier about. So this talk is something also, like Dave's talk, concerned with philosophical issues to do with constructionism. But perhaps you can understand it best from the perspective of these two words I have at the top. One which will be very familiar to you, the word computing, and another which may not be so familiar to you, which is the word construing. And to give you a little bit of background, the idea of construing is about trying to make sense of things. It relates somewhat to perhaps the theme which Dave talked about, the reasons for things, giving a reason, giving an explanation. So, context for the work is a project, an EU project that I'm leading at the moment, which is a way of using the computer, in which the emphasis is on what we call making construals, rather than writing programs. Now, when I was preparing this paper, I found some very interesting references from Papert, dating from the 80s, just a written transcription of some informal notes he'd sent to a conference on educational technology. And these were his comments. This is from the 1980s. The new technologies are very, very rich in providing new things for children to do. Then he says this interesting remark: a child who used logo to make a picture would be unlikely to say, I'm programming a computer. By implication, Hudnott was thinking they're doing something other than programming a computer. Constructionism can be that. He also makes this interesting remark: nobody knows how computers will be used in 10, 20, or 30 years' time. Well, of course we are 30 years on. My feeling, what is a sort of cue to what we're thinking about in our project, is that even today, it's very hard to think. But at the bottom level, what we're doing when we're dealing with computers, if we have to explain it, we have to explain it in terms of programming. And I don't think that's a very satisfactory state of affairs. It doesn't fit well with what Papert intended for constructionism, it seems, when he says we really should have other visions for how to use a computer, and using logo shouldn't be thought as programming a computer. So, of course, it's a very bold thing to talk about trying to use the computer in any other way than writing programs. We've got the sort of foundations of computing provided by traditional computer science, computational thinking, Turing, this sort of stuff. It's a big thing to try to justify a claim that there's something different from writing programs. But I want to say that making construals is essentially different from writing programs, and in this short talk I want to try to put a bit of context around that and give you a little bit of motivation for believing it by showing you something practical at the very end. So, two parts which are developed in our paper. First, I want to talk about a particular stance on construction that's different, a rather different way of thinking about construction from the way we normally do, I think, a philosophical stance. And secondly, to talk about some principles and an environment that is built for construction that isn't a program-like environment, isn't an environment that's simply one for writing programs. Now this is where I think some of the things that we talked about earlier are quite interesting. When I'm talking about constructivism, I'm referring to particularly to the work of Bruno Latour. This is not Piaget, and it seemed to me from what Dave was talking about this morning that probably this is a different vision of constructivism from Piaget's in some sense. But for the purpose of this talk, we think about Latour's concern is to say, what does it mean to construct things? And he's concerned about this in terms of what is the nature of the activities, of the agency that works in the world. Think of the things in the world as behaving according to natural laws. They have an agency of their own. that's one way in which we can try to explain the world around us, that it's obeying rules and so on. But obviously the mind and our own sense that we have a free will and opportunity to do things ourselves gives us an openness to our sense of agency, and there's a contradiction between these two. So the two is of the opinion, in his idea of constructivism, that there's a process of construction in which both the human and the natural engage. And things are constructed in that way. But for him, what is intensely problematic, and is discussed in a very humorous way in his paper, is that on the one hand, some people are very wedded to the idea that everything in this world is on the basis of rules, it's all natural world. And some people are wedded to the idea that it doesn't really matter what accounts for agency, what sort of reasons and explanations you give. Well, again, I don't want to dwell on this, but this is trying to talk about the stance that informs our work in a philosophical sense. I'm taking my inspiration from William James, writing over 100 years ago, and his position is very much in keeping with this idea that we shouldn't simply see things in terms of natural law, unless, if you like, or uncertain. James focuses on this idea that all of knowing we have is rooted in things we can experience, connections we can make in our own experience. So everything he wants to talk about in relation to our knowledge, he would root in personal ability to make a connection between one thing and another. And a good example, a simple example, one that we all understand, I think, is the connection between a word, the words we use in a language, and the things they might designate in the world. So if we understand a language well, then we personally make a very strong connection between a word and something it denotes. To the extent that I'm not, as I speak to you now, I'm not thinking about the meaning of the words as independent of the meanings. The utterance and what it refers to are one and the same thing. So James has a whole load of ideas about what these connections we directly experience can range over. And it's a vast number of things. The fact, for example, that I can see Dave and I can see Gerard in the same room, I can think of them as individual experiences, if you like. This is Dave and that's Gerard, but I can see you in the same room. And that's something given to me as an apprehension of connection between two things. So what we're proposing to do is to think of construction with this objective of trying to use computing technology to make these connections in our experience. So doing this directly is where we're heading. What's very valuable about this rooting things in our primitive experience is, first of all, there are all these quotes from James which show that he's taking very seriously the value of the mind, what the mind and the personal experience does here. In particular, at the end here, he's saying we shouldn't be concerned with what the absolute transcendent nature of agency is. We shouldn't really be bothered about whether there are rules that govern the way the world works. That's not the issue here. What we have to be concerned with are the things that come from our personal experience. And but that's the first part of what I said, what we have to do to make construals. That's to think about a different way of thinking about construction. So this, I hope, will be a bit more friendly. I want to now say something about the new principles and the new environment of construction that we've built that works with that in mind. So here's a sort of fundamental diagram, and you'll see that it has something to do with experience. This is the personality of the person who makes sense in their own experience between something they experience on the computer and something they see in the world. If you want to get something tangible to think of something like a spreadsheet, where you sit and look at a spreadsheet, which is just, after all, a bundle of squiggles on a screen, but you think of it in terms of some other external situation. Like you think, this is my bank account, you think about real money, and you don't consciously make that connection, just in the same way as words symbolize things in the world. So how do we support that in our computing context, when we think in terms of different kind of abstractions from computational thinking, we think, in the first place, our objective is to make this connection in experience. And we do it by building something on the computer which, in some sense, imitates whatever we want it to refer to in the world, or something that emerges in the world that's independent of the computer experience. And this has to do with observables, dependency, and agency patterns of these things that we see. We build these up, and in order to establish this connection, we also have to think about the context in which that takes place. So if, for example, in my spreadsheet analogy, it's not just enough to say, look at the spreadsheet, it refers to this class of students, you will be able to make that interpretation. Of course, it's important that that class of students really exists in the world, that they're within the right context, that it's this year's set of students, that they aren't all dead or all fixed. And all these things are crafted in the development that we make when we use the computer within our environment. So, this is a big mouthful to get across in 20 minutes, but let me give you a simple example of what a construal might look like, and how this links with, think of the previous picture, keep this in your mind as I do this. Sorry. I'll do this backwards now. But in this previous picture, what I'm showing you is a picture of something we can build, an artifact that's corresponding to something experienced in the world. So, on the top there, I just have a few icons that convey the idea of what, think first of what a child might see if they see somebody using money. They see that somebody takes something out of their purse and puts it on the counter to buy something. So all they actually see is that some obscure tokens are moved from one place to another, and that creates some kind of context. That's one personal apprehension. It's very mystifying to the child to know what this really means. But to the adult who does it, there are all sorts of other things going on there. We capture those by, as observables, we write definitions for them and maintain their values here. They convey things like, what money do I have available to spend? Do I have enough money in total to buy whatever it is that I want to buy? What's the money that I've offered? What change do I expect? So this is what's running through the mind of the adult person who might be using the purse. The child will just see what's at the top there. That illustrates the idea that ignorance, the other to knowing in a very unfamiliar sense, a very narrow, limited sense. So, in order to build up such artifacts, we have created environments which, this is the most recent manifestation of one, not quite, I think it's close to being. The general idea is that inside this window, we can input definitions of observables, so we build up descriptive observables by inputting them through here. We can then inspect these observables, find out what their values are through interfaces like this. We can see what they might describe, what experiences they might offer us by looking at canvases which are embedded in here. And then we might have things like sets of definitions which are saying how we propose to move from one situation to another, for example. How to represent changes that we need to do, interactions we may need to do. And this whole thing is put in the context of something which can explain and lead you through this in a kind of worksheet style or walking style. So those are the main ingredients of our environment. So the first thing, the thing is labeled A, there's the input window. The symbolist will tell you things about what the current values of observables are. Then you see the visualizations. Then you have some kind of narrative with embedded script fragments to tell the story of how this construal is made. And what I've done in this case is to take the first construal, which I gave you a little bit of context about, put it in conjunction with another model that's built from scratch inside this environment that represents a vending machine. The valuable part, one of the powerful things about building things in this way, is that we can do what we can do in the world, which is to take our purse and look at the vending machine and see them together. So putting these two things, juxtaposing them, is just putting together the two scripts. What is the connection with James here? Well, all the activities I'm describing here are things which are available for you to try online, certainly in Prototype. I'll give you a link to them at the end. When you come to do that, say, vending machine purse example, then we elaborate it for you in such a way that you see that you're building up connections in your experience, in that environment I just showed you, where you're studying, say, how a rectangle is affected by the parameters. And progressively, the connections you make become richer and richer in the spirit of construction. So that eventually, the constructions are talking about things that are really quite interesting to do with real-world significant things about purses and vending machines. Okay, so the final example I have, there are 3 examples in the paper, different aspects of construals. The third one was inspired by primary programming in Scratch, the kind of thematic thing, issues that Ivan was talking about this morning. So here's a Scratch program, which is intended for giving change. In order to think of this in terms of what must a child observe, the observables that they might make, in order to be able to give change. And we want to know what connections they have to be able to make to give change. So we can make a construal that will explore those issues. Now, this is what our construal looks like. I would quite like to show you it in action, but I probably will have a moment to do that just at the end. But first, let me try to pull it apart a little bit. So, when we want to give change, we think of a certain amount that we're going to have to specify, so we initialize the problem, and then we have to have some little agent which does the activity that the program would normally do of taking away the largest denomination coin that's available to us, displaying that, if you like. So this is the action that will produce the coin list. Time 2 minutes? Okay. Then this here is an observation, a group of observations which will determine which is the next coin we ought to output here. And then there's this piece, these definitions, which say how we ought to visualize the coins. So each of these elements you can explore for yourself online, but broadly I've taken each panel and tried to explain it to you. This is a very different thing from a program. It has program-like behavior, but it's vastly more flexible to use. So I need for you to look at this online. I might, if I have a moment, just demonstrate something to show that it does work. But these are the general ideas, that the virtues that this has is that you get very flexible agency in execution when you do this. You can blend the manual and the automatic. You can explicitly talk about delays. One of the features we have now in this environment is that we can do this kind of live coding, change values, and see directly how that affects the displays. By separating the agency from the context, we're able to freely change the way in which the agents act. What is particularly interesting about it, I think, is that we can link this to how we might think about a child's capability for giving change. When we write a traditional program like fill bags, it takes a very simplistic view, I think, as we've replicated here, of assuming that the child could say, what is the maximum value coin that I can take to give this amount of change. But that kind of level of observation is very sophisticated, and in reality, we would much prefer to try to understand better, in the spirit of constructionism, how a child can get to that word stage. And that means prototyping other kinds of activities, for which this environment is very well suited. Okay, that's it. So, just to summarize then, computing is what's appropriate when we're very confident about agency, when we know exactly what we're trying to use. We're trying to apply well-known, well-rehearsed and understood agency. Construing is about feeling our way where we don't understand what agency we really do. And what we're doing in our environment is trying to bridge between the two of these, to bring them together. Okay.
question.
I'm still wondering about the word construing. Construit sounds.
Maybe just a comment. I really like this idea of construing in the sense that you phrase it in the end when you're uncertain and confused about agency, and that relates to the last presentation, not the last one, but the one before, where we have tendency to focus on, like, in the space of reason, like if everything we know what we do, and this is not always the case, it's often not the case, and this kind of wanting to play in the openness of not being sure of what we're going to do with that or where it's going to lead us, I think this is something that is very interesting, and I want to see more of that.
But this is where James, I think, is very interesting from believing that we have explanations and causes in any absolute sense. He's all for encouraging us to think about telling ourselves stories. Some of these stories are very compelling and very useful, and that's fine. And that's where I think it fits in very well with your talk.
Yeah.
You know, what's the right sort of mathematics? Well, it's
the
just
temporary effect of
yes.
it too, because it might work for some time and then things change and it doesn't work anymore. An explanation is not a good one anymore.
Absolutely, yes. So I find this very compelling, that James is getting away from this fundamentalist idea of there is an explanation, separating the world into these two things.
Any further questions? Yes.
Hi. I was just wondering about the example that you gave from Philberg
Yes.
activity. But how practically would what you've developed be used in conjunction with? Would you use yours first to introduce that kind of activity, or something?
Well, here it is running, okay? It's easiest if you can do this for yourself online. But to give you a little bit of an idea, it's set up now so that, I hope it is anyway, money that I need to return. And it's set up in such a way that this agent says, when you click, and when the amount is bigger than something or other, when the amount left to give is bigger than 0, then simply add a coin to the coin list and update the picture. That's what that is doing, okay? So every time I click on here, this should produce the next coin in the system. But you see, I can do all sorts of things here. I can say what denominations are available to me. If you can't read it, but here it is, it's 1, 2, 5. Okay? So if I said, well, I haven't got, what would be sensible here? I say I haven't got a £2 coin. So I can just go in here and say, I haven't got a £2 coin. So, let's just check that's right. Then I can execute that, and I can restart this process. And now I say I haven't got a £2 coin, and lo and behold, it comes up with £1 coins. Okay? But I could also say, well, I don't like this kind of agency, which is, you can find this field quickly. Somewhere here, there should be another one. Well, let's go down here. I can go in here and say, I don't really want the click to come into the picture. And I think it's even better if I don't really have a weight. So I'll comment out this weight here. Okay, and then I execute this. Now what happens, so I can go in here and say, I can put this thing called live coding on here. Oh, my new laptop doesn't have a touchpad that works with a mouse. I can go do this, okay? So now, down here, I change this amount, and you can watch the columns will change automatically. Because now I've got a greedy agent. Doesn't wait, doesn't need to wait. So I should be able to do something like sit on here and say, move this. I hope I can anyway. It's a bit temperamental. Okay? But now I'm changing the amount, and as I'm changing the amount, it's telling me the changing coin. Accomplished person with British currency, that's exactly what happens. That you, as soon as you see the money, you know what the coins are. So that's in favour of embracing a lot more than the back algorithm does.
Great, thank you very much. Well, plenty of food for thought for this morning's session, and now it is time for lunch. And I'd like to thank our speakers very much. Sorry for the very bad English. I'd like to thank our translator, back in the room. And I'd like to thank you all for being a fantastic audience and asking some really interesting and thought-provoking questions. Lunch will be on the, please grab some lunch and take it with you. Okay, so thank you very much, everyone.
We have three presenters, Anna, Karina, and who is this? And all are present, that's fine. You have 20 minutes for talk each, and then we have at most 10 minutes for discussion. We start with Anna Isabel. She gives a presentation. It is a common work with others, and about generalization processes and experience using Expressor with primary school children. So you will explain what it means.
Okay, thank you. Okay, I'm actually presenting on behalf of Christiane. She was supposed to come, but then last minute we all got our grants cut off because of severe economic problems in my country, in Mexico. So I already had a plane ticket, so I was not coming, fortunately. Even though I have to pay for it. But. Okay, so her talk is called Generalization Processes, and you already read it, so I'm not going to read it again. So this is about early algebra in a Mexican primary school. And in the Mexican, how many of you are familiar with early algebra? Okay.
Yes.
Okay, good. So in the Mexican curriculum, the teaching and learning, I don't know what it's like in other countries, but the teaching and, sorry about the spelling mistake, the typo, the teaching and learning of algebra starts in 7th and 8th grade because it is argued that it is very difficult mathematical content, so therefore it's not available, it shouldn't be available to early ages, that's the assumption. But early algebra does focus on algebraic thinking that bridges arithmetic ideas and patterns with fundamental algebraic ideas such as the idea of unknown, a variable, function, equations, inequalities, etc. And when you do early algebra, you focus on the thinking processes that lead to algebraic ideas, even though they are not totally finished or are not completely expressed in formal algebraic language. And there's a lot of literature on early algebra. One route is to do proportional numerical and geometrical reasoning, and another is generalization processes, and we're going to focus on the second one. And Bernard and colleagues, he give 4 approaches to the teaching and learning algebra through generalization processes. First, generalization of numerical and geometrical patterns, and modeling of mathematical situations and of concrete situations, the study of functional relationships, and the solution of problem equations. And the discovering patterns requires 3 processes. One is activities with numerical patterns, another is expressing rules that characterize particular numerical patterns by means of sentences involving students in making clarifications and precisions, and the third is promoting that students express rules in short form. So these 3 processes are the things that were used in the study I'm presenting. And so the study was a study for introducing early algebra in Mexican primary schools by designing and implementing sequences of activities with a software expressor. How many of you know of expressor? Okay, good, because I'm going to present. In order to generate early algebraic thinking, specifically generalization, in primary school students of grades 5 and 6, that would be ages 10, 11, more or less. So expressor is a constructionist microworld. It was developed at London Knowledge. It's a free Java-based software, and it was part of a project that they had in England, also with colleagues from, I think, from Greece. And it seeks to provide students with a model for generalization that could be used as a precursor to introducing algebra. And it follows Papert, sorry, it's very small, but maybe you can't read very well. It follows Pappert's constructionist paradigm because it provides several approaches for students to be able to construct their own mathematical models. In Expressor, students can build patterns of figures, of color square tiles, and Expressor rules underlying them. And they can work in a numeric, geometric, and programming environment and make use of patterns or regularities correspondingly to their inputs when they create a program and make sense of what they are doing when they validate their prediction. That is, children can construct these patterns of tiles and colors and encapsulate them in the form of blocks and shapes that they can repeatedly reproduce by giving rules for shifting the block in the horizontal and vertical directions, as well as for how many times they repeat the block. So I'm going to, let's see if this works. This is a video. It's 4 minutes, but I think I have time. Let's see if it works. And if it doesn't, I'll go outside. Maybe I'll try to run it outside of the PowerPoint. Okay. It's just an introduction to Expressor, so you get an idea what it's like.
These are various activities students classrooms. For this tutorial, you will choose the activity, build your own model with no help. Let's open it. Adjust the construction area and the windows as you like. You can place tiles onto the construction area by clicking Tile Generator, then dragging and dropping the tiles where you like. Let's build a flower like this. Then you can group tiles to make a building block. Click on the highlighted tiles and select Make a Building Block. Now you can make a pattern. Type numbers in the number generator and drag and drop them to replace the question marks. Then choose how many repetitions of the building block you want and replace the last question mark. Notice that what you do with the construction area is mirrored in the general model. Your pattern is not colored. This is because you have not answered the question, how many tiles? There are 5 yellow tiles, so you
Hooray, it worked. You can also gain numbers. Notice that in the general model, you can see the random values assigned to the unlocked number. Now you try to build a model like this one.
Okay, this is just to give you a glimpse of, and it's built explicitly for expressing algebraic concepts, like
you see, was this a multiplication or what was, which operation was done?
I was paying too much attention to. You want to see? I can put it there.
It's
It was multiplication, yes.
So, how many times? Okay.
You can build an in this case, you need to add the expressions for the numbers of green, red, and yellow tiles. Let's try animating them. Hooray, it worked.
Okay, understand.
You can also
So you're multiplying the pattern, okay?
notice that in the general model, you can see the random values assigned to the unlocked.
Oh, I can't see my mouse. Where is it? Okay, so in our study, we had 30 students from a public primary school in the somehow the fifth and sixth years of elementary school. So these are 10 and 11-year-olds in Mexico City. So before working with Expressor, we had children do a questionnaire that aimed at exploring their ability, strategies, and difficulties in the identification of geometric and numerical sequences, as well as if they were able to understand the rule for constructing sequences in several ways. And these are just a glimpse of the questionnaire. And so there were 8 questions. Some had focused on arithmetic increasing and decreasing sequences. The second on comparing the growth of an arithmetic sequence, concomitant variation, linear variation, y equals 2x plus 1, the exponential variation from an arithmetic sequence, stating and solving an equation such as x plus x over 3 equals 1200. And so those were the questions in the questionnaire. And the questionnaire revealed that most of the students were acquainted with numerical increasing and decreasing sequences, but they did not continue sequences through the negative values. That they were able to give a rule on the number of sticks. If we ask them how many sticks you need to, there's a question on that. Needed for a given number of triangles, so they had to build with like sticks, a triangle. At different degrees of generality, answers such as count the number of sticks, there are multiple, use a 3 times table, or for 4 I need 12, show that some students were in transit from additive to multiplicative thinking. And then the inversion of a particular item in the series presented some difficulties, even though it reduces to a division without remainder, the following transcript is not included in the PowerPoint, I just realized. I just got the PowerPoint this morning, so I didn't have much time to look at it, sorry. So the second stage of the study focused on a didactic sequence on generalization processes that was structured using worksheets to be done with Expressor. And so children worked in pairs with Expressor and were asked to draw designs that were in the worksheets. And there were 2 activities. The first one was called My First Pattern with Expressor. And here children were asked to build a simple block to reproduce a pattern shown in the worksheet. And they had to record the results from the My World window. If you remember, Expressor had 2 windows. There was on one side and then on the other. And they had to record their results on the worksheet. So here's a glimpse of the questions. And they're all in Spanish here, but I can't read here, it's too small. So group your tiles by dragging them into the red rectangle and so forth. So then they had to build patterns such as these. And so I can't, it's too small here, I can't read. Okay, I don't know how to do this. And so what happened was that the students became familiar with building it to right, or M down, or which, these, by the way, is a notation that is used in the expressor microworld. So, or, n times exclamation point, or to say things like moving the blocks n places right, n places down yields a pattern. For left and upward shiftings, they use negative numbers, which they hadn't used in the initial questioning. So this showed that there was some improvement, some development of algebraic ideas. The second activity was working in the general world. So the first one was working in my world. This is generalizing. And I'm going to try to see if I can show you both this. Let's see if I go like that. And then I can read it from the... So here in this activity, it says, in this activity we will show you how to build a rule that will allow us to color the pattern in the general world of expressor. So build a pattern like the one shown in this figure. Its construction block was repeated 4 times. Color the pattern indicating to expressor the number total of mosaics that are necessary. What happens to the pattern if you modify your data? For example, if instead of repeating the block 4 times, you repeat it 5 times. Use expressor to fill out a table such as the one that is shown down below. I know you cannot see, sorry about that. Remember you must, well, this is technical, just release the block to see it easily. So how many times do you repeat the number, the block? So in the table it says 3, 5, 2, 0, 7, 9. Number of tiles, it's already filled in the tiles, so it's 12, 12, 6, 0, 21, 26. And the question is the pattern colored? So those are the things that they have to answer. And then in the next question, which you cannot see because it's cut down, maybe if I don't know if I hide one of these bars, maybe you can see it. Okay, yeah, a little bit. I'm just trying to do both things simultaneously, so it's a bit hard. It has, instead of, the last thing is just asking whether the pattern is colored. So you have a similar table like the one you had, oh, no, I can't. Sorry, I cannot show you. So you have a similar table to the one you had before. I'm going backwards, aren't I? There, like this one. But the last table is filled. The last, not the column, row. The last row is filled with yes, yes, yes. And so you have the number of times that the block is repeated, and then the student has to fill out how many tiles. So those are the kinds of activities that were given in the so now I'm going to try to go back to this. Let's see if this works better. So some of the things that the conclusions from the study were that the early activities in both, this combined both the worksheets using paper and pencil and the expressor. And that the expressor software is a powerful tool for initiating in algebraic symbolization and for developing generalization-related ideas. However, the key point in using this software is to take advantage of its property of integrating the numerical and geometrical context within a structured didactical sequence guided by the teacher, or facilitated, we would say here, that combines activities and materials in two contexts, paper and pencil and espresso. So I don't think I can answer presenting for her because she couldn't come to the conference. So if you have any questions, please email her. Her email is in the paper. And I did my best at trying to present. Sorry if it was a bit confusing. I didn't have time to actually she sent me the PowerPoint when I was already traveling, and I didn't have very good access to email, so I only downloaded it last night. So.
Thank you. Thank you, Anna. And we can have a discussion anyway. We don't need to ask questions. Yes, we can discuss what we have heard. I think these generalization processes, it's a good way. I think it's a usual way how to learn. You have first some special cases and then generalize. I think this is a way of learning, isn't it?
Yes, I
Yes, you don't have to answer. It was a question to the auditorium.
That's actually the session before lunch was talking about just those types of things. Moving maths session.
Yes.
And about taking things that we do from our experience